So today we are going to discuss the waves on a string. Suppose we take one string here. We need to fix the string at one end. If we are disturbing in the other end, what would happen? Suppose if you are holding this other end, if you are just oscillating up and down, the string will oscillate, then the mechanical wave propagate through the string. So if you are look at the string, it will be looking like that. So the way it is propagating like that. So it will move from left to right, then it will hit at the fixed end, then it will reflected back. Again the wave move from the right to left to right. So if you are continuing oscillating the string, the wave will propagate from the left to right to left, left to right. So this setup will form the waves on a string. So what are the observation if you are looking at this configurations? There is a speed of the waves. The speed of the wave, we can take the mechanical wave on the string, the speed of the wave, we can take it is a v. Then the another observation, we are giving the force. So the force we can take the force F. So if there is a force, then there will be acceleration. The acceleration we can take on the string is A. The mass of the string, we can take the mass of the string is the small m. Then the string is having linear mass density. So the linear mass density, we can make the linear mass density, we can make it's a mu. In general, the linear mass density mu is defined as the mass of the string divided by the length. Maybe if you are taking the length, it will be smaller. Now what's our aim means? Here we are going to find what is the speed of the wave. So we can ask one question: what is the speed of the wave on the string? That is our main motive when we are studying about the waves on a string. Now our question is, what is the speed of the wave on the string? So for that purpose, we are going to take the small cross section of the string when the wave is propagating with a speed v. So the small cross sections, I am drawing it here. So this is a string. If you are taking the small curvature on the string when the wave is propagating, this is the zoomed version of that portion. You can fix because it's looking like a arc of the circle. So you can fix the center point. This center point from the arc, that is called the radius of the curvature. So here at this end as well as this end, because it's a string, so what it will do, there will be two tension force. It will be acting on each end. The tension force I am calling it's F. That it will be acting like that. So the angle with the horizontal, the tension force it's making, it's a theta. Here also left hand side, the tension force is making angle, it's a theta. So this component of the force is F cos theta. This component of the force is again the F cos theta. Here from this end, from the center, it's making the angle theta. From the left end of the string, in the small cross section, and the center is making the angle theta with respect to the the bisection of the arc. So from the right side it's theta, the left side that's another theta. Now we can calculate the linear mass density, because the small section, assume that the small section of portion of the mass of the string is m, the linear mass density is mu. So now we can calculate the length, the arc length of the small portion. It will be equal to the arc length that will be equal to it's a radius times the angle. So the r times, it should be 2 theta. So r times 2 theta. Then we can calculate the linear mass density. The linear mass density mu, it is equal to the mass time the arc length. So the arc length is r times 2 theta. The mass of the string m equal to, if you are rearranging this one, it will give the linear mass density time 2 times r theta. This is the mass of the string. We can take this equation number 1. Next, if you are considering this shape, then the force, actually the waves, it will set up this portion. To maintain these portions, there will be a centripetal force acting on the string towards the radius of the curvature. So this centripetal portion, it will be acting each section when the wave is propagating in this manner. There will be definitely centripetal force. So the centripetal force from the Newton, according to the Newton law, so according to the Newton law, the centripetal force is the Fc equal to mv square by r, the radius of the curvature. Without this force, there is no curvature on the string. So if the curvature is there when we are giving the when the wave is propagating, then there will be a centripetal force mv square by r. Now the centripetal force, if you look at the picture in the previous slide, there is a one component is a parallel f cos theta acting along this wave propagation directions. Then there is another component, it will be acting f, the sine component acting towards the center of the centripetal force. So there will be a two end, there is a two tension force. So f sin theta, f sin theta. There will be 2f sin theta acting towards the center of the small arc length. So the net force towards the center acting on the string of small curvature, the net downward force acting towards the center is 2f sin theta. Suppose if theta is small, we can make the small angle approximation. Sin theta is approximately equal to theta. So for this case, it will be equal to 2f theta. This is equivalent to the centripetal force. So there is a Newton force, there is a tension force. So these two are equivalent when the wave is forming on the string. So if you are equating these two to f theta equal to m v square by r. Already we derived the mass of the small portion, that way from the equation 1 the equal to nu times 2r theta. So 2f theta equal to mu times 2r theta, that is the mass of the small portion, times v square by r. We can cancel this or this r. So left hand side 2 theta, right hand side 2 theta also we can cancel. The finally the f equal to nu times v square, or the velocity of the wave on the string, the velocity of the mechanical wave on the string is, so the v equal to square root of f by mu. So this is a way we can calculate the velocity. Once if you know the force, then linear mass density, we can calculate the speed of the wave on the string. So this relation is true because when the wave force is huge, or if you are oscillating the string with a huge force, then the acceleration will be huge, then the velocity of the wave on the string will be large. But on the other hand, if the mass of the string is large, or the linear mass density is large, then definitely the wave velocity on the string will be small. So it is inversely proportional, one is directly proportional. So that's a square root. This is the way we can calculate the speed of the wave on a string.